you have been introduced to the notions of sequences, limits and continuity of a multivariable function, in particular a function from R2 to R. Now, as you have done in your calculus 1, you may be assuming that what we are going to do next is that we are going to define the notion of differentiability of a multivariable real valued function. So recall what was the definition of differentiation or derivative of a function when we talked about single variable real valued function. So suppose we had a subset D of R, and suppose that C was an interior point of D. Now a function f from D to R is said to be differentiable at the point C in D if the following limit exists. So this is now you are very familiar with this limit. So you compute the functions at C plus H, compute the function at C, and take f of C plus H minus f of C divided by H, and take limit as H tending to 0. So if this limit exists, we say that this function is differentiable at the point C. And in that case, if the limit exists, then we denote this limit by the quantity or by the expression f prime c, and we call f prime c the derivative of f at c. Now we are going to take our first baby step towards understanding what could be the possible notion of differentiability of multivariable functions. Of course, here we are going to restrict our attention to the case when the function is of two variables. So what do? We start with a subset D of R2 and we take x0 y0 a point, just like we have taken C over here. And analogously, let us for the time being assume that this point x0 y0 is an interior point of D. But I will come back to this this thing, why we need an interior point, or more generally why we do not need an interior point in order to define the notion of partial derivatives. But I will come back to it in a moment. So a function f from D to R, a function of f from D to R is of course a function in two variables because D is a subset of R2. So the function f from D to R is said to have a partial derivative with respect to x at the point x0 y0 if the following limit exists. So if so you take f of x0 plus h comma y0 minus f of x0 y0 divided by h, and you take limit h tends to 0. So if this limit exists, we denote it by del f del x x0 y0, or simply f suffix x at x0 y0. So let me write it here, del f del x x0 y0, if after all this exists. And in this case we are going to say that this function is going to have a partial derivative with respect to x at the point x0 y0. You could do similar thing for the variable y, so there is nothing special. So I have just copied and pasted the definition which I have given above and changed x to y wherever it was required. So again we pick a subset D of R2 and take a point x0 y0, which is again an interior point for the time being, and a function f from D to R is said to have a partial derivative with respect to y in this case at the point x0 y0 if the following limit exists. So here what we did, here we took the expression f of x0 plus h comma y0, we replace it by f of x0 comma y0 plus k minus f of x0 y0 divided by k as k tends to 0. But then you might ask, okay, so let me complete this. So in such a case, if the limit exists, we of course say that this has a partial derivative with respect to y at the given point x0 y0, and we denote this limit by del f del y or f suffix y, just as we have done above, del f del y at x0 y0 if at all the limit exists. So then you might ask that why I am so sure that f is defined at points which are of this form. So here the notion of interior points come into picture. So suppose we have a region like this, which is our D, and suppose this is our point x0, y0. So what we are doing is that, so this point is x0, y0, and if I want to pick up a point whose coordinate is x0 plus h comma y0, then we just draw a horizontal line, and then this point or a point like this will be of the form this. But this, since this is an interior point, there is a small disk around this point x0, y0, such that this disk is contained inside our region D or our subset D. So an existence of an interior point guarantees that for all small values of k here and h here, these quantities are defined. So just to make the discussion complete, so how would this point look like? This point will be on a line which is vertical from the point x0, y0, and it will be somewhere here. So this point will look like x0 plus y comma y0 plus k. But then we come back to the question where we really need the point x0, y0 to be an interior point. You can see that whenever we are going to talk about the limit which relates to del f del y, we only need that the points that we are looking at should lie on a vertical line which passes through x0, y0. And similarly, when we are considering this limit as h tending to 0, this quantity, then all we need is a small part of a horizontal line which should be contained inside our region D. So this is what I have written in the remark here. We do not really need the point x0, y0 to be an interior point. It is enough to have a horizontal line segment containing x0, y0 to be contained inside D. So written as a mathematical statement, there should exist an art which is positive, such that all the points x comma y0 such that x lies between x0 minus r to x0 plus r, this set should be contained inside D. So as I have just said, that to define the partial derivative with respect to x at the point x0, y0, all we need is a small part of horizontal line which passes through x0, y0, and that must be contained inside our set D. Similarly, when we are going to talk about the partial derivative with respect to y, so this was related to del f del x, and when we are considering partial derivative with respect to y, all we need is a vertical line segment containing x0, y0 to be contained inside D. So as I have mentioned before, we only need a small part of a horizontal of a vertical line segment to be contained inside D. So let us summarize what we have done. If the following limits exist, then we denote. So if the following limits exist, then we say that this has a partial derivative with respect to x, and if this limit exists, then we say that it has f has a partial derivative with respect to y at the points. So at the points point x0, y0, and we have the following notations. So let us proceed. So what are the possible geometric interpretations? So you have seen that somehow differentiation in one variable calculus corresponded to what is known as the slope of a tangent line at the point C, or tangent to the curve C at the point at the point x0, y0. So what happened in calculus in one variable was that if we were given a function fx, then we would just plot y equal to fx, and if it was our point C, then f dash C would be the slope of the tangent at the point at the point c comma f of c, at the points c comma f of c. So this point is nothing but c comma f of c. But then what should the partial derivatives imply? So this is simply the following. So suppose I draw our picture, the graph of the function. So suppose that I have been given a function f of xy, and what we are going to do is that we are going to simply plot the graph of z equal to f of xy. So suppose that this looks something like this. So not necessarily it should be like this, but suppose in our case it looks something like this. So suppose that we want to compute the partial derivative. Okay, so I must give you what are the x, y, z coordinates. Suppose this is our x axis, this is our y axis, and this going above is our z axis. So suppose that we are given a point x0, y0 in R2 in the domain. So then this should correspond to a point f of so this should correspond to a point x0, y0 comma f of x0, y0 on the graph of the function. And suppose we are going to talk about del f del x at the point x0, y0. What we do is the following. So here we are going to say that, so suppose we are considering fx at x0, y0. So we are going to take a plane y equal to y0, which cuts the graph into which cuts the graph of the function into a curve. So how should y equal to y0 look like? So suppose that this is our point y0. So we should take a plane which passes through this, and this cuts our picture into a graph. So I do not know what is there, but there should be a two-dimensional graph, and this looks like a curve. So then then del f del x or fx x0 y0 is the slope of the tangent line to the curve cx that we get. So at the point x0 comma y0. I hope this is clear. And then what we do for fy x0 y0, the argument is similar as well. So cy is the curve which is obtained by intersecting the graph of f by the plane x equal to x0 in this case, and then fy x0 y0 is the slope of the tangent line to C at the point x0 y0. So this is quite simple. This can also be interpreted as rate of change of a function towards x direction or towards y direction, but let me not talk about those asides here. So computationally, how do you compute the partial derivatives of partial derivative of f at x0 y0? So I'm going to talk about fx x0 y0 or del f del x x0 y0, and del f del y x0 y0 or fy x0 y0 can be defined analogously in terms of y. So what we do here, we are going to take y as a constant here. So whenever we are given a function, we are going to just put y equal to y0. So in that case we are going to treat this function f. So we have a function and we want to define the partial derivative with respect to x at this point. So to do that, what we are going to do is that we are going to put y equal to y0. So put y equal to y0. So then this becomes a function with respect a function with the variable x, and then we just differentiate this function with respect to x. So this is what we are going to do. So what is del f del x at x0 y0? we are going to put y equal to y0. So then we get a function with in variable x, and we are then simply going to differentiate with respect to x, and of course we are going to put x equal to 0 afterwards. So similarly we can define del f del y at x0 y0 as follows. We are going to take f of x0 comma y, then it becomes a single variable function in y. We are going to take dy of that, and then we are going to put y equal to y0. So that's about it. Let me proceed. So then just in the previous discussion you have seen that del f del x at x0 y0, del f del y at x0 y0, this comes just as differentiation of a single variable function. So sums, products, quotients, and compositions of functions. So if you want to take the partial derivatives of sums and products and quotients and compositions of functions, they can be obtained in exactly the same way that you have done in the case of functions of one variable. Okay, so one new definition, this is called gradient of a function. So suppose that f is a function from d to r2, and x0 y0 is a point in d which satisfied the condition that we needed for partial derivatives to exist, at least not the limit, but there should be a horizontal line passing through x0 y0, and there should be a vertical line segment which passes through x0 y0. So that's all we need, and this line segment should be contained inside our region D. So in such a case, if the partial derivatives exist, both the partial derivatives exist, then we define the gradient of f at x0 y0 as follows. So we denote this by this notation. So gradient of f at the point x0 y0 is going to be defined as fx x0 y0, fy x0 y0, and of course you can see that these are going to be two real numbers, so the resultant is going to be an element of two-dimensional Euclidean space. So we will come back to more usage of gradients later. So let me give you some examples of partial derivatives, some easy examples. So suppose I take f of xy to be x square plus y square, then you can see that the partial derivatives exist at all the point. So let us look back at our recipe on how we computed partial derivatives. So suppose I want to define suppose that I wanted to check whether the partial derivative of f exists at the point x0 y0, or we want to simply compute it. What we do is that we will take f of x comma y0, this becomes a single variable function. We just do a differentiation with respect to x and then put x equal to x0. So then what is this function f of x comma y0? F of x comma y0 is simply x square plus y0 square, and it should be evaluated at x equal to x0. So this is going to be 2x, and it is going to be evaluated at x equal to x0. So this is nothing but x0, 2 times x0. But then similar calculations go through for fy as well, and if you want, you may please check these examples, check these calculations from your first definitions as well. So all you need to check is limit h tending to 0, f of x0 plus h comma y0 minus f of x0 y0 divided by h, and what should these expressions become? So these expressions will look like x0 plus h whole square plus y0 square minus x0 square minus y0 square, and what you are going to do, you are going to divide this by h, and so you will see that you are going to be, so let me do the full calculations here. So x0 square plus h square plus 2x0h plus y0 square, and then minus x0 square minus y square divided by h. You can see that, so y0 square, so these are going to be cancelled to each other, these are going to be cancelled with each other, and all we are going to be left with is h times h plus 2x0 divided by h. So by simple limiting argument, these are going to be cancelled with each other, and all we are left with h plus 2x0, and this tends to 2 times x0 as h goes to 0. Okay, so we have also checked our calculation properly in terms of definitions. So let me now look at another example. So let us look at this example. F of xy, it is given by the positive square root of x square plus y square. So the first observation that you can make out of here is that the function f is continuous. So it is very easy to check that this function is continuous. I leave it to you as an exercise, especially the part where you have to check the continuity at the points x0, y0 which are not equal to 0. So you may, for example, apply the notion of compositions of functions. Continuous functions is continuous. So let me not go do this, but let me check these things. So suppose that x0 y0 is not equal to 0 0. So then what happens? We see that fx x0 y0 is given by this quantity, fy x0 y0 is given by this quantity. So in particular, these things are non-zero, and this partial derivatives exist at all points where x0 y0 is not equal to 0 0. Now what happens if you take x0 y0 equal to 0 0? So let us do all the calculation completely. So we are going to take f of h comma 0 minus f of 0 0 divided by h. So since h comma 0 is not equal to 0 0, we are considering limits. So this is going to be the positive square root of h square divided by h. F of 0 0 is equal to 0, as you can see, and it would turn out that this is equal to limit of modulus h divided by h, and you have seen in your calculus 1 that this limit does not exist, and this implies that fx at 0 0 does not exist. Now similar calculation will show you that fy 0 0 does not exist. So okay, so this you are going to expect, I mean, it will not surprise you too much, because it is okay to have a function which is continuous but not differentiable. So this is something you are getting here, that you have a function which is continuous, but there exists a point where none of the partial derivatives exist. But what happens with the converse? So is it true that if x exists at, so if f is a function from D to R, and if you take a point x0 y0 with required properties, so then if you are given that fx x0 y0 and fy x0 y0 both exist, then is it true that the function f is continuous at the point x0 y0? So here you are going to see a surprise that this is not true. But you know that if you are talking about a single variable function, then differentiable functions are always continuous. So here is a counter example. So suppose you take f of xy, which is given by xy divided by x square plus y square, if xy is not equal to 0 0 and 0 if xy is equal to 0 0. Then you have seen in our lecture on continuity that such functions are not continuous, but it easily turns out that this function has the partial derivatives with respect to x and with respect to y at the point 0 0. So this is all about partial derivatives for the time being. We are going to talk about higher order partial derivatives and differentiation of a multivariable function in our upcoming video.